students. Here we are on lab day, ready to participate in the energy lab. In fact, today we're going to be doing two activities. We're going to be doing the energy lab on page 58 first, and then we're going to be doing the classroom activity, a modified version of it, on page 59. So let's get started right away, shall we, on page 58 with our lab activity. And the first thing I'd like you to do before we even begin is, while I'm introducing this energy lab, I'd like you to look at the graph. Look at the graph on your page, and I'd like you to add the values here in terms of words for the x-axis and the y-axis. Woo, where's the y-axis? There's the y-axis, and the x-axis. We're not even going to use numbers for this particular lab activity. We're just going to use words, relative words. And the words that we're going to be using along the x-axis are the relative masses: light, medium, and heavy. So notice the lines on your graph, and I'd like you to label those lines now: light, medium, and heavy. And over on the y-axis, we're going to be plotting the relative velocities, not with numbers in this first activity, but rather relative words that we can just observe: slow, medium, and fast. So take a moment to label your x-axis and your y-axis in the manner I have indicated here, and perhaps you're already done with it, so we can get started. The problem of the lab activity reads as follows in your book. What is the relationship between mass and velocity if kinetic energy remains constant? What is the relationship, if any, between mass and velocity if kinetic energy remains constant? Now, we're going to be creating a line graph here in order to answer that problem. But let me just explain what the problem is asking you. Basically, you have learned this week that kinetic energy equals 1/2 mv squared. Yeah, great formula, right? But what does it really mean? Is there a connection? Is there a relationship between kinetic energy, mass, and velocity? Don't say it out loud yet. Think about it. Is there a relationship? What today's lab is going to be illustrating to you is that if we keep the kinetic energy the same and we alter the mass, what kind of an effect, if any, will that have on the velocity? So the problem is asking you, if we keep the kinetic energy the same and we change the mass, is that going to have any effect on the velocity? And if so, what is it? So take a moment, pause me, and write your hypothesis as I head over to the close-up lab. All right, we're back here, and we have our apparatus set up in front of us. We have a little plastic track here set up with a catapult launcher. And this catapult launcher, let me show you how it works. The catapult launcher is hooked up to a device that gets pulled back and is held in position by a little notch. And right now there is a rubber band which is storing energy. And what kind of energy is stored energy? Potential energy, that's right. Right now, this launcher has potential energy because the rubber band is stretched. When I push the button, I'll move this over just a little bit so you can see it a little bit better. There we go. When I push the button on the launcher, watch what happens. Boo! The launcher is put into motion, and whatever is in front of the launcher will be put into motion. And what is energy in motion called? Kinetic energy. So this little device enables us to control the amount of kinetic energy by pulling back the same distance each time, thereby giving the rubber band the same potential energy for each of these 3 trials. And every time we push the button, it's going to be the same amount of kinetic energy propelling something. So what is it that we're going to propel? We're going to propel a little sled that I made out of popsicle sticks. And on this sled, we're going to be putting little presents that we need to deliver to someone. And these little clay presents have a mass to them. Now, we're not even going to use numbers for this activity. We're just going to observe. We're going to watch the 3 trials. The first trial, the sled is going to be empty, so it's going to be light. The second trial, we're going to put one of the presents on it, so it's going to have a medium mass. And the third trial is going to have the 2 presents on it, so it's going to have a heavy mass. And what you need to do is to observe whether the velocity of the sled is slow, medium, or fast. And you're going to write down in your books the appropriate word. Now that you've labeled your diagram, your graph, you're going to put into your observation section the appropriate word for mass and velocity, and we're going to plot the words. So are you ready? Let's begin. So trial 1. We're going to pull the launcher back. It's got a certain amount of potential energy. When I push the button, it's going to have kinetic energy. And we're going to begin with an empty sled, so our mass is light. So for trial 1, write down that the mass is light. Okay? Here we go. Now, watch the sled. I'll count down from 3, 2, 1. Boing! Did you see it? I'm going to do it again so that you can see it a little bit better. So we pull back, potential energy. When I push the button, kinetic energy. Here we go. 3, 2, 1. Boing! Hopefully you saw it that time. Now don't write any words down yet. Just watch the 3 trials because the velocities are relative to one another. So you can't really write down a word until you see the other 2 trials. So we're going to pull it back again. And now we're going to put 1 present on, so our mass is now medium. Trial 2, write down for your mass, medium mass. Medium mass, trial 2. Now let's watch. Let's see what kind of velocity we have. 3, 2, 1. Boing! Let's do it again. Same amount of kinetic energy. Ready? Here we go. 3, 2, 1. Boing! Did you get it that time? All right, now for the third trial. The third trial, we're putting 2 presents on, so the mass is heavy. Trial 3 mass, heavy. And now let's watch our relative velocity. 3, 2, 1. Boing! Let's do it again. Heavy mass, velocity 3, 2, 1. Boing! Now again, for the velocities, you're writing down simply the words slow, medium, or fast. So I'm going to do this one last time in reverse so that you can make a relative comparison. Here's the heavy sled. Relatively speaking, is it slow, medium, or fast? 3, 2, 1. Boing! Now for the medium mass, only one present. In 3, 2, 1. Boing! And finally, the light mass with no presence in 3, 2, 1. Boing! Write down the appropriate words now, slow, medium, or fast, next to, or rather under, the appropriate masses on your data table, and then you're going to take that information, draw a line graph. You're going to plot the 3 data points, draw a line graph, and interpret your graph, write a conclusion, and then discuss your conclusion with your class. You can pause now as we get ready for the next activity. All right, hopefully you had some good discussion there. And based on the shape of your graph, hopefully you were able to make a conclusion as to whether there is a relationship between the mass and the velocity if the kinetic energy remains constant. Keep that in mind for tomorrow's quiz. And now let's get to the other activity on page 59. Our activity on page 59, we're going to modify here a bit. And so you don't even have to really read the procedures. I'm gonna give you new procedures here, but I do want you to do something to the graph. The graph in your book, you're going to be adding an additional line at the end of your graph. I'm going to leave this graph in view for you because I'd like you to write down the x-axis and the y-axis as you see in this picture here. And while you're copying this down, I'm going to share with you what it is we're going to do in order to create another graph, another line graph. So this one we're calling the ball drop activity graph. And in this particular activity, I'm going to use a bouncy ball, a bouncing ball. And in the lab, I've already done this, and I'm going to show you a video of it in a moment. I am going to be altering or changing the potential energy of the ball by dropping it from a different height. And you'll notice on the y-axis, the height is measured in meters. So we're going to be dropping it from 0.25 meters, 0.50 meters, 0.75 meters, and finally 1.00 meters. Now, don't say it out loud, but based on your current level of knowledge and understanding of potential energy and kinetic energy, again, don't say it out loud, but think about what do you think will happen to the kinetic energy, which we're going to be measuring in terms of the height of the bounce, the movement of the ball after it hits the tabletop. What effect do you think increasing the potential energy will have on the kinetic energy? Again, don't say it out loud, but if you read the problem at the top of the page, it says, what is the relationship between potential and kinetic energy? I'd like you to write a hypothesis as you pause me now. All right, we're back here, and I'm going to be doing this activity for you so that we can be socially distanced and we're not sharing any materials. And you'll notice that I have a meter stick behind me, and I've labeled the meter stick. If you're watching this on a smaller screen, Might be a little bit tough for you to see the numbers, but I'll tell you that each tab is 0.1 meters from the 0 mark. At the bottom is 0. This is 0.1, 0.2, 0.3, 0.4, 0.5, all the way up to 1.0 meters. And I'm going to start this video and try to gather the data on your own, but don't worry, I'll give you a summary of it when we're finished here, just to make sure that you get the data correctly. So let's play this video from the beginning. And as you can see, once again, I've got the meter stick on top of a tabletop, and I'm going to be using a little bouncy ball. Actually, it's a pretty big bouncy ball. Hi, Mr. Skirpst. Everybody wave to Mr. Skirpst. There we have the bouncy ball, and I'm going to start at 0.25 meters, and I'm measuring from the bottom of the ball. So look at the bottom of the ball as I drop it. Oop. How high do you think it went? All right, if you didn't get it, don't worry. I'll give it to you in a moment. Now I am dropping it from 0.5 meters high. Watch. Hopefully you were able to see how high it bounced. And by the way, I even slowed this video down so you could see it a little bit better. Here we are from 0.75 meters. Whee! Hopefully you got a chance to see the height bounce on that. And finally, from 1.0 meters, watch how high it bounces. Great. Now, even if you didn't catch those numbers, thank you, Mr. Skirpst. We'll see you later. Even if you didn't get those numbers exactly, you don't have to worry about it because hopefully you got to see the relationship. So think about that in your heads. You know, if numbers scare you, don't worry about it. Look at the relationship between how high the ball started and how high it bounced as a measure of the relationship between potential and kinetic energies. And now we'll go to the next slide and I'll give you the actual data. And this data you can actually copy down in your books. Copy down in your books on page 59 for trials 1, 2, 3, and 4. Trial 1, the height, which we're using to measure potential energy, was 0.25 meters. And the bounce height was 0.20 meters. Trial 2, the drop height was 0.50 meters. The bounce height was 0.35 meters. Trial 3 and trial 4, you can see the relative numbers there. After you have copied the numbers, what I'd like you to do is take those numbers as your coordinate system, your X and Y values, and plot those 4 points on your graph, and then connect the dots with a line and read the description under the graph to help you write your conclusion. So you can pause me now to plot your dots and draw your line, and let's see how you made out. Hopefully when you plotted your dots, your graph looked something like this. Your dots were arranged, all 4 of your dots were arranged this way so that when you connect the dots, you have a diagonal line. It's not a horizontal line, it's not a vertical line, it is a diagonal line. With that in mind, again, read that little description under the graph that you've just made to determine what the answer to your problem is as you write your conclusion. Once you've written your conclusion, you'll have some time to discuss this with the class. And don't forget that tomorrow we have a quiz on energy. So be sure to study everything we've gone over this week. And so as you're discussing these 2 activities today, I'm simply going to say for now, bye-bye.